So yeah, like I said, my name is Cam. I'm a now second year DPhil or PhD student here at the University of Oxford, and my research is focused on developing new sustainable and biodegradable plastics that we can use particularly for elastomers or more rigid engineering plastics. And as my talk goes on, I'll come to talk about that a bit more. So the theme for the British Science Week this year is growth, and so as we're living in a rapidly growing world with a rapidly growing population, and one where there's a greater demand for a higher quality of living, there's an increasing demand on plastic. As I'm sure you're all aware, and as we'll touch on later, plastic has a lot of issues surrounding it in terms of pollution and waste. And so as we move forward, we will have the same reliance on plastics and polymeric materials, but we need to find a greener way of producing them and using them. Before I get into all that, like Patricia did, I'm going to give a little bit of background about myself. I am from North London in Enfield, and I went to my local comprehensive school called Highlands. I did my GCSEs there, and I stayed on to do my A-levels, where I did chemistry, physics, maths and further maths. I loved London and wanted to stay there, like Zoe touched on, I went to UCL, or University College London, and did a 4-year degree, which is an integrated master's, so you leave with a master's degree in chemistry. And it was here that I had my first real experience with chemical research. I was lucky enough at the end of my 3rd year to be awarded a little bit of funding to do some solid state chemistry with Professor Robert Palgrave. And then for my 4th year, which is where you do a research project, I worked with Dr. Claire Bakewell, looking at photoswitchable catalysts to control the polymerization of sustainable monomers. And this was my first real exposure to this field and developing new sustainable plastics. And it's something I really enjoyed, it's something I became very passionate about, and I knew I wanted to continue that moving into my PhD. So I applied to come to Oxford to do my PhD, or DPhil. Oxford just has to call it something else to be different, in inorganic chemistry for future manufacturing. And I'm at Trinity College, Oxford, which is a very pretty building here, and I'm in the Williams group, which I'll come to explain what that means and why we're called that and what we do in a tiny bit. Yeah, but before we come to that, I just want to sort of clear up some sort of myths or maybe some misconceptions about what chemists do on a day-to-day basis. Because I think when I was studying my GCSEs and my A-levels, between 16 and 18 years old, I knew I liked chemistry, but I don't think I knew what a research chemist did and what that work entailed. So when I talk to my friends and family, I often get a lot of them not really understanding. So I'm still convinced that my grandparents think that I'm trained to be a pharmacist and fulfilling prescriptions, which is obviously very important work, but not what I'm doing. My parents don't trust me to look after the family barbecue in the summer, so they become a pyromaniac and I'm just blowing stuff up and burning things all the time. Thankfully, that's not what I do. I like to think I'm relatively safe in the lab and look after everything. And then my non-chemist Breaking Bad, and with all of these things, this just isn't true, and this isn't representative of what I do and the work that I take part in. So what is it I actually do? Well, as I touched on, I'm in the Williams group, and we're called that because we have a principal investigator, our supervisor, Professor Charlotte Williams, who's a fantastic and very inspirational chemist. And she leads a team of chemists you can see in this picture here. It was taken a couple of weeks ago. A very multidisciplinary, very diverse team. We've got people from Spain, Mexico, Canada, Australia, Germany, Italy, China, America. It's a hugely incredible, diverse team. We've got Netherlands here, and it's a fantastic environment to be in. And we're all focused on looking at one big problem, and this is how do we make new sustainable plastics and polymers? So our research focuses on the study of metal complexes for use as catalysts to make polymers, fuels, and new materials. So we spend our time in the lab, each being like a different aspect of this problem. So I'll come to talk about the specific work that we do in the second half of my presentation, but I want to sort of touch on a bit of background of polymers and of plastics. I'm sure a lot of you will have covered this in your GCSEs or A-levels or equivalent qualifications. But in case there's anyone who hasn't, or just as a quick recap, we'll go over that now. So polymers are long chain molecules made up of much smaller molecules. And these chains are called polymers, coming from the Greek poly meaning many and mer from meros meaning parts, so many parts. and monomers, which mono means one, so one part. So polymerization is the act of linking all of these monomers together to form this very long chain. And you can think of this as paper clips all being hooked together to form one very long chain. And the way that chain of paper clips moves, behaves, is very different to the individual paper clips themselves. And that's essentially what we're doing when we make polymers. But like with all chemistry, nature got there first and beat us to it and mastered this whole world of polymers before we even knew what was going on. So there are examples of polymers everywhere in nature. DNA and proteins are examples of polymers. Cellulose is everywhere in the natural world. These are really sophisticated, very advanced materials, and ones that we can only dream of replicating this kind of precision and control in their structure. But the kind of plastics that you're probably most familiar with are these kinds. So the most common application probably for plastic is as packaging. You can all go to the supermarket these days without seeing the majority of items coming in some form of plastic packaging. And these could be food, detergent, cleaning products, healthcare products. The beauty of plastic is that it's cheap, it's lightweight, it can be colorless, it can be see-through, it could be any color we want, it can be any size and shape. We can tune its properties to be hard or soft, flexible, rigid. We have this whole spectrum of different properties we can choose from to tailor towards particular applications. But really, this packaging is only the tip of the iceberg of where we use polymers in our everyday lives. Two big examples are in our technology. Probably the device that you're watching this talk on right now is packed full of different polymers, from the casing to the keyboard, to the screen, to the electronics inside. There are polymers everywhere. And I'm sure that everyone watching this talk today is wearing some kind of a piece of clothing with a synthetic fiber in it. That could be nylon, it could be a polyester. They've become a pivotal part of the clothing industry now. And another key example of the importance of plastics has really been highlighted over the last couple of years with medical applications, particularly with the COVID-19 pandemic. Without plastics, we wouldn't be able to deliver life-saving COVID-19 vaccines through the synthesis of syringes. And plastic is also really key for PPE, so personal protective equipment that people need to wear in everyday lives, or particularly in the healthcare sector. And this is because, again, plastic is cheap, it's lightweight, it can be see-through, and this makes it ideal for wearing for long periods of time, or for producing single-use syringes to deliver vaccines. So plastics are used in a whole wide range of applications and everywhere in our lives, and they become a real cornerstone of our 21st century lifestyles. But the word plastic has quite a few negative connotations attached to it, and I want to sort of find out what you guys think of plastic. So if you go to the Slido, there should be a poll open for you to put in one or two words that come to mind when you hear the word plastic, because there's a lot of connotations, good and often bad, and I just want to see what you guys in the audience think. So if you scan that QR code, or if you go to the hashtag on Slido, you should be able to see that poll. So if many of you could fill that out as possible, that'd be really interesting to see. I'll leave this QR code up on my slides for the next for a couple of slides or so to give you a chance to fill that in. In the meantime, I'll come on to talk about the common ways that plastics are made. And in industry, the materials that we use are typically made through two particular polymerization techniques. And you might have heard of these. The first is addition polymerization, and this is where we take our monomer, represented here by this red ball, and we react it with a catalyst, and we can chain these red balls together to form one long chain. And in reality, this monomer, this example here, is ethene or ethylene, and this is just two carbon atoms with a double bond between, and each bonded to two hydrogen atoms. So when we catalyze this to form our polymer, this is how we denote it, where we've opened up this double bond, and so now these are connected to two other carbons, and we write this in brackets to indicate this is our repeat unit, where n is the degree of polymerization and the number of those repeat units that we have. And this is the typical this is polyethylene, and this is what's often used in plastic carrier bags. So you've probably all interacted with this hundreds of times in your lives. And the key about addition polymerization is that you can see every atom in our monomer is now in our polymer. So we have 100% atom economy here. And I just wanted to show you this kind of notation, which you may or may not have seen depending on where you are in your education of chemistry. This is what we call the skeletal notation, and we use this in chemistry a lot because we're really lazy and we don't like drawing out all the carbon and hydrogen atoms. So here we say each point is a carbon atom, and then depending on the bonds, the number of bonds we have, we assume there's the right number of hydrogen atoms. So here this is ethene, and here there's polyethylene, which is essentially a zigzag. The second most common way that polymers are produced in industry is through what's called condensation polymerization. And there's a few key differences here. The first being that first we have two different monomers, shown here by the red and the blue ball. And we have a catalyst that can enchain these in an alternating fashion. And here we also produce our polymer, but also another small molecule. So what's going on here? Well, typically our two monomers are what we call diacids or dicarboxylic acids, meaning they have two carboxylic acid functional groups, and dialcohols, meaning we have two alcohol functional groups. And these two groups can condense together, so one acid with one alcohol can condense to form this ester linkage here. And in doing so, it kicks out one molecule of water. So this is how we form this alternating chain of acid and alcohol to form our polyester. And as you can see that we've got other types of atoms involved now. We have oxygenated polymers, which are really important in terms of sustainability and degradation, as we'll see later. And here I've shown this polymer and these monomers in their skeletal notation again, just to try and get you guys familiar with this if you've not seen it, for some of the structures that I'll show later in my slides. Okay, so I hope you've all had a chance to head over to Slido and fill in that poll. Okay, let me just quickly stop sharing my screen. And I will, sorry, give me one sec. Share again, see this work. I have lots of different answers here, which is great. Okay, so we've got lots of answers. McDonald's bags useful but problematic. Plastics everywhere and a shock emoji. Plastic straws horrible. Plastic bags recyclable useful. Polluting the ocean, hashtag Team Seas. Unenvironmentally friendly, non-biodegradable. Limitless, that's interesting. Terrible, life-saving. Interesting, life-saving, useful. So this is the first time I've sort of seen some nice positive comments here about plastics, but yeah. Chocolate wrappers, a crying emoji. Yeah, so you guys have sort of hit on a lot of the key aspects, or sort of at least society's key ideas around plastics, which is really interesting to see. But also, yeah, some of you, like I touched on earlier, noting that plastics are really useful. So that's really interesting to see. So thank you so much for filling that out. It's genuinely very interesting for me to see that. So let me just share my slides again. And fantastic. So yeah, thank you for saying that and for sharing those ideas and thoughts with me. It's genuinely really interesting, and I think you guys sort of have seen a lot in the media about plastics and are fully aware of the problems that they represent. And so just to touch on some of the numbers surrounding that, so these are some stats from the last few years. As of 2018, there were 359 million tons of plastic produced by humans in all of history. As of 2015, apologies, 359 million tons of plastic were produced in 2018 alone. The numbers are so big it's easy to get confused. And as of 2015, humans had produced 8,300 million tons of plastic in total. And these are just numbers and sizes and quantities that we can't comprehend in our day-to-day lives, to be honest. And of that 8,300 million tonnes, 6,900 is already waste. So that's sitting in landfill or in our oceans, as you guys were mentioning. But there's a very small part of that, and only 9% of that plastic has ever been recycled. That's at least been recycled once, so it might have been, a plastic bottle that's been reused once and then thrown away. And so it still could be sitting in landfill today. So that's a tiny, tiny proportion of this huge quantity of plastic produced. And while we always think of the plastic pollution in our oceans, in our seas and the waterways, it's important to highlight that plastic pollution is also responsible for enormous quantities of carbon dioxide pollution. So the plastic industry produced the equivalent of 200 coal-fired power plants of CO2 in 2019. That's enormous quantities of carbon dioxide. And as I'm sure you're all aware, CO2 is a greenhouse gas and is a key driver in the anthropogenic climate change that we're seeing in our increasing global temperature. So there's a lot of problems with the current plastic situation. We've got pictures here where you can see what we think of in terms of what might be in a landfill or in our seas. And there's this great article that came out by David Schuckman last year about how it was actually just 20 companies producing half of the single-use plastic in the world. And you might be thinking, we have paper straws now, you have to pay 20p to get a carrier bag. You know, in the UK, we're cutting down on our use of single-use plastic. And generally this is true. We have been getting better at being aware of the not using single-use plastics and finding more sustainable alternatives. But this is quite unique to the UK and maybe Western Europe. But actually, the developing world has this increasing reliance on single-use plastics because it's clean, it's hygienic, it provides a better quality of life. And actually, this has resulted in the global trend of plastic pollution being an increase. Some of the what we call petroleum to virgin polymer plants, so this is making plastics fresh, if you like, from crude oil. Some of these companies are producing the largest plants the world has ever seen. So there's no slowdown in plastic production. In fact, it's the opposite. It's accelerating very, very quickly. And yeah, this might be shocking and might be a bit depressing. As we see here, you know, these a very famous image from David Attenborough's Blue Planet, where we can see lots of tiny particles of plastic waste floating in the top and the surface of the Pacific Ocean in this case. Another thing we have to consider with plastic pollution is the formation of microplastic or nanoplastics, which are tiny particles of plastic that have been worn away and eroded in the same way that pebbles on a beach are worn down. And the scary thing here is that we don't really understand the impact of microplastics on the environment and on our own health. There's been plastic found in fish in markets either side of the Pacific Ocean. There's been microplastics found in the drinking water in Western Europe. These things are tiny, they're really hard to filter out, and we probably all have lots of these tiny particles inside us right now, and we just don't know the long-term health implications of these. And as I touched on, we had been making progress with reducing our single-use plastic pre-pandemic, but the pandemic has set this back slightly. So this was an article at the peak of the coronavirus pandemic back last year. And this is talking about how there's 100 million single-use masks being discarded every single week in the UK alone. So obviously it's these huge quantities of plastic and material that's going to persist in the environment for a very long period of time. And reading about and hearing about these problems can be very overwhelming. It can be quite depressing, and it's like, oh, what can I do? Nothing's going to work. But I want to spend the rest of my talk discussing some of the solutions and steps that scientists are taking today to try and remedy some of these problems and try and reverse some of the damage that plastic pollution has done and develop new materials moving forward. So I want to talk through sort of three core solutions. The first one is that we need to develop new sustainable plastics. And I put this image up here and I call it the Holy Grail because I particularly love this image. It sort of represents what we call a closed economy of plastic production, so closed loop, so that we have our raw materials here. So these can be plants, it could be waste products. I'll give a few examples of these in a bit. So we could take a plant, we could extract a monomer from that, and we could produce a polymer. We could make a material. So this is a synthetic material that comes from a natural resource. With that polymer, we can fulfill a particular application. So that polymer could be used for a whole host of different products and used for varying amounts of time depending on that application. And then when that polymer reaches the end of its life as a product, it can be recycled or reprocessed. So in the same way, I'm sure you'll have wheelie bins outside, you put your plastic in there. They often go to facilities where they can be separated, melted down and produced and turned into new plastic products. So you have your water bottle, it's melted down, turned into more water bottles. This is very effective. It's quite difficult to do still. We need to get a lot better at it, but it works. The key limitation with this kind of recycling being that actually we damage the properties of our material every time we recycle it. So at the end of time, eventually, no matter how many, after so many recycling cycles, you get to the point where it has to be thrown away. And ideally, we want a material that can sit in the environment, could sit in the soil, and over time, not thousands or tens of thousands of years, but within a few years or a few months, can break away into environmentally benign products that can actually potentially even fertilize plants, which is some really interesting research going on at the moment. Like I just mentioned, we need to get much better at recycling plastics. We're really, really poor at this generally as a planet, and we need to get much better. So this picture sort of shows 5 key recycling cycles. The first being using raw materials as a kind of recycling, because we can grow a plant in theory indefinitely and keep harvesting a monomer from that. We could reuse a product, so once it reaches, we've used it once, we can take that same plastic product and just use it again. That's a form of recycling. The type of recycling that you're probably most familiar with is what we call mechanical recycling, and this is where we melt down and reprocess our material, which like I mentioned, it works, but it's time consuming, it can be costly, and it can damage the properties of the product over time. And then there's chemical recycling. This is a very sort of hot area of research in the field at the moment, and this is the idea where we take our polymer and we depolymerize it. So we take our long chain of monomers all stuck together and turn it back into the monomers that it was formed from. And we can very, very easily separate those chemically, and then we can repolymerize those to produce a new product which doesn't have that loss in properties. And then finally, as sort of a last resort, we can burn our polymer essentially if there's no other recycling options available, recover the energy from that combustion, and couple this with what we call carbon capture and utilization technology, so we burn it, the CO2 release can be captured, and then we can either store that to avoid it going into the environment, or we can use it for something useful. The third point I want to touch on is the sort of key solution is that we need to get much better at understanding how plastics degrade, because we want to design materials that degrade in a way that we can understand, we can control. So this is what a polymer looks like if you were to zoom in really close. It's like a ball of spaghetti with all these chains entangled together. But as we zoom out, the picture is actually a lot more complicated than that. There are regions that are harder and more crystalline, there are regions that are more amorphous, and this builds a very complicated picture of what's going on. And as we're trying to understand degradation, we need to understand how that's happening at every length scale. And obviously this produces a very sort of complicated and messy picture, but if we want to understand how plastics and polymers degrade, it's key that we get a much better understanding of this. And the goal here would be to produce materials that could degrade on demand. So you could have I'll use the same example, plastic water bottle, you could drink from it, it would be fine, it can last on the shelf for ages, but as soon as it's been sent to the recycling plant, they can be like, okay, we're going to put it under these conditions and it's going to degrade instantly. And we can then recycle that chemically or mechanically or in whatever way you would like. So these are sort of 3 core solutions. There are many, many others. It's a very complicated issue to deal with. But I'm going to sort of touch on the first one of those in terms of developing new sustainable polymers. And this is what we do in the Williams Group and what my research project is particularly focused on. So there's a class of polymers called thermoplastic elastomers, which are used in a whole host of different applications, from the soles of your trainers to any kind of stretchy material similar to rubber bands, insulation of electrical cables, or even like the sticky adhesive parts on sticky notes and sticky tape. And these are typically formed of what we call tri-block copolymers, meaning that there's actually almost like a polymer sandwich with two different types of polymer either side of another type. So we call these ABA block copolymers. And what we do here is we choose a polymer for the A block that is very hard and very rigid, and one for the B block that's very soft and flexible. And what we can do is by chaining these together is we get both properties. We get a material that's flexible, extendable and stretchy, but also has really good mechanical strength because of those harder blocks on the end. And these materials do something quite interesting in the solid state. In the same way oil and water separate when you mix them together, the different blocks like to separate out into where like is with like. So we have regions of A shown in the red and regions of B shown in blue. And these are different what we call morphologies. So they have these spheres, these cylinders, this very complicated gyroid structure, lamella, which is essentially just like layers of the blocks. And these different morphologies have give very particular properties. And by tuning how long these blocks are, the monomers we use, the ratio between the two blocks, we can tune our morphology and therefore tune our properties and therefore the application that material could be used for. And so in our group, we're particularly interested in sustainable monomers. So these are ones that either waste or come from nature. We have terpenes, which is a class of material that come from lots of different plants, like limonene, which comes from lemons and oranges, pinene, which comes from pine trees, menthol, that comes from mint. You can see we're not very original with the naming here. We can have vegetable oils, these long fatty acids, which can be turned into polymers. Carbohydrates are very popular. Polylactic acid is actually the most popular monomer for biodegradable plastics. And maybe you've seen plastic cups that say it's biodegradable. That's probably made of this monomer here called polylactic acid, which comes from corn. But in particular, of all of these monomers, we're most interested in carbon dioxide. And this always seems as a waste, as a gas and causing climate change, but actually we're interested in using it as a monomer. We actually want to do something with it and do some chemistry. And we carry out what we call ring opening copolymerization, where we react CO2 with an epoxide, which is this kind of molecule here. We have oxygen in a three-membered ring to form polycarbonate materials. And these can be used when they're very short chains to form polyurethanes, for elastomers, foams, coatings or adhesives. Or if what I'm particularly interested in, if you get to high molecular weights of very, very long chains of these polymers, you can create rigid plastics and elastomers. So this is really exciting because we can take this material that's waste, super cheap, and turn it into something useful and add value to it. So this is a particular example from a paper that was published in 2020 by our group. And this is an example of a catalyst. You often hear about catalysts when you're studying chemistry, but you don't often see many examples of them. This is one developed by our group, but we have zinc and magnesium coordinated in this what we call macrocyclic ligand, because it's this big, essentially, ring. And it's attached to these two phenol coligands, but you don't need to worry about those. What's important is that this catalyst is able to carry out the ring opening polymerization of this monomer, which is called decalactone, which comes from castor beans, or castor oil, which comes from castor beans. So again, another renewable feedstock. But then we can switch the type of polymerization to ring opening copolymerization of CO2 and epoxide. And by doing this, we form our soft mid block to start with, and then grow on the hard blocks either end to form our ABA block copolymer. And this is a really exciting material. It's got a very catchy name of polycyclocarbonate block epsilon decalactone block cyclohexene carbonate. And this, I've drawn out the full structure of this polymer here. So you can see we have an initiator in the middle, our polydecalactone block here, and then our polycyclohexene carbonate blocks on the end. And this material is so exciting because we can tune its properties really easily. So by changing the amount of carbon dioxide we have in there, we change its properties and therefore the applications it would be good for. So at just 6 weight percent of carbon dioxide, we have a very soft, sticky adhesive, but it's also very strong. It's actually much stronger than any of the adhesives or tapes on the market today. If we got to 9% CO2, we make a much harder material, so it could be freestanding, but it's very stretchy. These are great elastomers. And we go up to 16% weight of carbon dioxide. We can make much harder, much more rigid plastic. So you can see here, unlike stretching like this, we sort of see this whitening, which is called crazing, if you want the technical term. But this is like much more like the plastics you probably encounter in your day-to-day lives. The key other very interesting aspect of this polymer is that it's packed full of these carbonate and ester linkages. So these points are sort of like weak points, if you like, in the polymer, or points that we can target when we want to degrade it. Because of this oxygenated backbone, we can put our polymer in some mild conditions, maybe a bit of heating, some water with some acid or base, and we can start to break apart our polymer to produce diols, hydroxy acids, and carbon dioxide. So this, going back to the Holy Grail I showed earlier, this material is a fantastic example because it's made from materials coming from castor beans, which are renewable as a plant, and carbon dioxide, which is a waste material. We can make a interesting tri-block copolymer with those, and we can take that polymer and tune its applications by changing the weight percent of CO2 in there. And then we can either degrade it, like I talked about, with attacking those carbonate and ester linkages, or we could recycle or reprocess the material by heating it up, by recasting it, by pressing it. And so this sort of is a good step in fulfilling the Holy Trinity. And my project is actually taking these materials as sort of a first step in that and trying to advance these properties forward so that they're more competitive with the petroleum-derived materials that we encounter in our everyday lives. So to conclude, I know that's been a whistle-stop tour of the field and some of the work we do, but polymers are made up of long chains of smaller molecules called monomers. They're traditionally made through either addition or condensation polymerization. They really are these wonder materials that have extremely desirable properties, and that's why they are everywhere. They are such fantastic materials. But it's these same properties of these materials that results in it persisting in the environment for incredibly long periods of time and all these problems that we're seeing now. So we need new sustainable polymers comprised of renewable monomers, which are able to degrade. We need to improve how we recycle plastics. And we need to better understand polymer degradation. And in the Williams Group, we're all working hard to try and address different aspects of these problems to try and help enable a greener future for plastic. So before I finish, I thought I'd just give a few recommendations. I know most of the audience are GCSE and A-level age or equivalent, and maybe looking to apply to university. And if you're particularly interested in chemistry, that's why I assume you're here today. Here are some fantastic books I'd recommend. Stuff Matters by Mark Miodownik is fantastic about all kinds of materials. A similar book by Anna Pujajski called Handmade. These two are both authors at UCL, so I have particular allegiance to them. If you're interested in chemistry general or even just life, I'd highly recommend reading Primo Levi's Periodic Table. It's about the life of Primo Levi, an author and chemist who grew up in the north of Italy during the war of Mussolini, and as a Jewish man, his time at Auschwitz and his career in life. It's really, really interesting. I'd highly recommend that. Some podcasts related to what I talked about. The Infinite Monkey Cage is a fantastic podcast. I'm sure most of you have heard about that. Sciso Tangents is sort of a similar American version hosted by Hank Green. Radiolab covers stories across the whole scientific spectrum. And Life Scientific is hosted by Jim Al-Khalili, a professor of physics at Surrey University, where he interviews a different field-leading scientist every week and talks about what got them to where they are in their career. And I always find that really interesting. But if you're particularly interested in learning more about what I've spoken about plastics today, I'd highly recommend reading this report from the Royal Society of Chemistry. It's free to download as a PDF on their website. It's called Science to Enable Sustainable Plastics. And it goes into much more detail and depth than I could possibly do in this talk today. So I highly recommend that. And then all that's left is to thank a few people, particularly Saskia for inviting me to talk today, the Oxford Chemistry Outreach team for making this happen, my supervisors, Professor Charlotte Williams and Professor Clive Siviel, the Williams Group, the OxICFM CDT and industrial partners who fund my research, and you for listening. And if you have any questions you think of after the talk, please feel free to contact me on my email, which is cam.poon@trinity.ox.ac.uk. And yeah, now I'm free to take any questions on any of these things or anything else you can think of. So yeah, fire away.